You must have seen problems like these appear in Olympiad geometry. Weird diagrams, random areas, absolutely random. You don't know where to begin it from. They ask ratios for areas. Look at this triangle. Look at this one. Look at this one. How do you know what's the height? What's the base? Where do you think you'll begin this from? So, what are the techniques that are required to tackle problems of this sort? What theorems do you need? What observations do you need to make? What kind of lemmas you need to solve these problems? We'll be discussing exactly that. And with that, we'll be starting the episode 2 of Euclidean geometry. So, welcome everyone to episode 2. And if you remember, in the session 1 of Euclidean geometry, we did spotting congruent triangles. And we also did a couple of problems. And at the end, I introduced you to one of the techniques we use to make our problems easier, taking reflections. And today we'll do one more problem based on the same concept of congruency. Congruency. And I'll give you a glimpse into the technique of rotation through this problem. Here's the problem. You can pause the video and try on your own. I'll recommend you to try this using synthetic geometry approaches. We can approach this problem using coordinate geometry as well, which we'll be doing today. And of course, at first I'll tell you this and then this one, the approach second. So yeah, let's begin. This is the problem that we are given. We are provided with a unit square. Let me just draw it parallelly with you. So we have a unit square and there's this triangle inside the unit square. Here we go. From PC, we have the triangle. This is the unit square. All right. We are provided with points P and Q. We have to find this angle. Let's call this theta. The theta looks weird. Okay. All right. And we are also provided that the perimeter of triangle QAP is 2 units. We are supposed to find angle PCQ. While this is a unit square, so this length is of course 1. Now let's say this length AP is A and this is B. This of course is 90 degrees. Now if you try to spot some congruent triangles in this diagram, it's not very easy. You see, apart from this middle triangle, every other of them has a right angle triangle. And we're not really sure about these two angles. It's very difficult to spot a congruent triangle from these. So what we'll do is, we'll use the technique of rotation. Why? Because it's not easy straight away to spot congruent triangles. So what we'll do is, we'll force congruency. And how are we going to rotate this? We'll rotate what? We'll rotate triangle QCD. Alright, so I'll have to make you visualize how exactly do we do the rotation through this problem. So let me just bring the diagram down. Alright, perfect. So we intend to rotate triangle CQD. CQD, right? So instead of looking at the whole figure, I recommend you to look at the parts of it. What are the parts of it? We have side CQ, side CD, and DQ. Look at the diagram in parts. Let's say this angle is alpha, this angle is beta. We're rotating this triangle. So first of all, let's look at CD, this side. So let's say we have to rotate it by 90 degrees. So we'll rotate CD by 90 degrees. So I'll make a perpendicular. That will be the new position of CD. Let's call this D1. D got there, right? Now let's come to CQ. CQ will rotate CQ by 90 degrees as well. We have to rotate the whole diagram by 90s. So CQ by 90, I'll drop a perpendicular on CQ. Yes, and this will be the new position of CQ, the Q1, and we have D1 Q1 as the new position of DQ. Perfect. Now once again, we need to rotate it by 90 degrees. What our intention is, we have to make CD coincide with BC. CD coincide with BC. We have to turn this whole thing and bring it here. So once again by 90 degrees, we'll have something like this. Perfect. And once again, if we do by 90 degrees, we'll have this diagram. So this is what we need. This is the final position of what? Of Q, Q3, and D came here, coincided with B. Now, let me just change the color. I want you to look at two triangles. I want you to look at this triangle, this, and this. What are we calling them? CQP and CPQ3. Yep. Notice that CP and CP are common. This thing, right? Also notice that CQ, this is the triangle that we brought here, right? So CQ is basically this. CQ3 is the new position for CQ only. So this equals this. Now, we have S and S. What criteria can we have? Either we can have SAS or triple S. We don't really have much data regarding the angles here. So we'll stick to this. We'll have to focus on this one. What side do we have now? We have PQ and PQ3. Perfect. That is what we are supposed to make equal. Now if you focus on PQ, what do we have? Do we have any data regarding this triangle? The perimeter is provided to be what? 2. These sides are A and B, so PQ would be what? 2 minus A plus B. Now look at PD. PD, that is 1 minus A. And also look at DQ3. What is DQ3? DQ3 is basically the new position of DQ, because this is what we rotated here. DQ came back here. So DQ3 would be equal to what? DQ, and DQ is what? 1 minus B. Also notice that PQ3, this side that we are supposed to find, is what? PD plus DQ3, that is 2 minus A plus B as well. So we have these two sides equal as well. Perfect. Now we have triangle. Let me just once again shift the diagram. Alright, so we have triangle CPQ equals to triangle CPQ3. Perfect. This triangle equals to this triangle. Now, what do we do when we have two triangles congruent? We collect the treasures using CPCT, the corresponding parts. Can we say angle PCQ3 equals angle PCQ? Right? What is angle PCQ? That is theta. Also notice that since this is the same triangle as this, because this has been rotated here, so this angle is also alpha. The same angle is here, right? So we are essentially saying that alpha plus beta equals to theta. Notice from the square that alpha plus beta plus theta is what? 90 degrees. Now these two equations we have, from these two, what can we say? We can put theta in place of alpha plus beta. So we have 2 theta equals 90 degrees and theta to be 45. That's our answer. Perfect. Now a lot of people must be like really confused, like people were in the live class. How does one even think of something like this, something this absurd, like rotating this and then forcing a congruency and then coming up with the answer? You don't. Like a beginner is not able to think something like that. Of course, if you are able to think and you are a beginner, you're not normal. All right, a normal human cannot think of this. So what we do coordinate geometry. All right, so that will be our approach too for this problem. I won't be solving the whole thing using coordinate geometry. I'll just give you the hint for those who don't understand how we use, how we exploit coordinate geometry in synthetic geometry problems. I'll just shift the diagram. Perfect. So what we'll do is we'll assume the coordinates of this point for our convenience as 0 0. That means we'll assume that this is the origin. Remember that this distance was a, so let me just mark this a and this as b. So point P, the coordinates of point P is going to be a0, and of point B is going to be 1 0, right? Ignore this part now. We don't have to look at this. We have to look only at the square, the original diagram. And for this, it's going to be 0b and 0 1 here. And for C, it will be 1 1. Perfect. Now, what do we have to do? We have to find theta. What is theta? Theta is the angle between two lines. What are the two lines? CQ and CP. Have you studied something like this in straight line? For people who have studied straight line. For those who don't know straight lines, the angle between two lines, if theta is the angle between two straight lines, then tan theta is given as m1 modulus of m1 minus m2 upon 1 plus m1 m2. Now what is m1 and m2? M1 is slope of any one of the lines, let's say of CQ, and m2 is also the slope of CP. Now what is the slope? Let's say this is a line AB. Coordinates of point A are x1, y1. Coordinate of point B, x2, y2. So we have slope of AB, MAB, let's say, that would be y2 minus y1 by x2 minus x1. Notice that we have the coordinates of the edges, like the vertices, C and P, A0 and 1, 1, 1, 1 and 0, P. So we can find the equation from here. Now it won't be a very sweet looking equation. So we'll have to use one more condition. What's the condition? The perimeter one. The perimeter of triangle QAB was provided to be 2. We said that side QP is 2 minus, alright, 2 minus A plus B. We can also find the length of QP if you observe this triangle. This is a right angle triangle using the Pythagoras theorem. So I'll be doing exactly that. So I'll be writing 2 minus A plus B is also equals to what? Under root A square plus B square. Now I'll square both sides. I'll have this 2 square minus plus A plus B the whole square minus 2 into 2 into A plus B. So when you solve this, you'll get an equation which looks like a Diophantine equation, and it looks like very sweet. It looks like you can factorize it using the Simon's favorite factoring trick, but that won't really help. I tried to use Diophantine. It won't help because A and B are not integral. Alright, so don't waste your time on that. Use it on the tan theta equation that we had earlier from the equation of straight lines. And when you do that, you'll realize tan theta comes out to be 1 and theta will be what? 45 degrees. So that is how you exploit coordinate geometry in these problems. Alright, so coming to the second session, we'll be learning this technique of spotting cyclic quadrilaterals. Cyclic quadrilaterals. Now you must not feel like circle geometry came out of nowhere in triangles. This is something we'll be using in problem solving involving angle chasing and a lot other things. This is a very popular technique that we use. So it's important for you to know and understand this. And that is why I'm telling you. So I'm sure you know what a cyclic quadrilateral is. It's something, a quadrilateral, all four vertices lying on a circle. That is what you call cyclic. This is the easiest way to spot one, to recognize one. But you won't always have a circle to help you. So the first thing that we observe if you don't have a circle, is in a quadrilateral. Let's say this is a quadrilateral ABCD, and if the sum of the opposite angles they add up to 180, this and this, D and B, angle A plus angle C is 180, then the quadrilaterals are cyclic. So you don't need to have a circle, don't need to observe that A, B, C, D if they're lying on a circle or not. If this is happening, then the quadrilateral is cyclic. Now, coming to the second thing, that is the important one. Before that, I'll be telling you this theorem that you need to know. The theorem says that angles subtended by the same or equal arcs, chord, or segment at the circumference of the circle are equal. Now, you must be knowing what's a chord, right? And an arc as well. What's a segment though? This thing you see here, this is the arc, and this whole thing, this is the segment. This is the smaller one. You must be able to observe that this we have a bigger one as well. You call that major segment, and the smaller one as minor segment. And same goes for arcs as well. Now the theorem says that the angle subtended by the same chord or the same arc or the same segment, it's the same thing as you see. I can make them subtend angles at the circumference, right? I can make them subtend multiple angles, as many as I want to. The theorem says that all of them are going to be equal. So all these angles, theta, 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 these are going to be equal. That is what the theorem says. For now, I want you to just remember this. We'll be doing the formal proof of this theorem in circle geometry. For now, just know this. Now, coming to cyclic quadrilaterals, how are we going to use this to recognize, to spot a cyclic? So if I just draw the diagonals of a cyclic quadrilaterals, you'll be able to observe that AB, all these sides are acting as chords. And AB, if you look at AB, the blue one, it is subtending the blue angles. The same chord AB is subtending blue angles. So according to our theorem, they're going to be what? Equal, right? Same goes for the green one. Look at AD, the green one. It is subtending the green angles on the circumference. So these are also going to be equal. Same goes for the orange one and the sky blue ones. This one. So if you see something like this, if you see even a single pair, let's say this is something of this sort is given to you. Now if it is given that this angle is equal to this, then you should immediately conclude that ABCD is cyclic. You don't need to look for any other pair. If even a single pair is given, then that will make this quadrilateral cyclic. Perfect. That is how you spot. This is the most important one. People struggle at this one, so you need to focus better. Now based on this technique of spotting cyclic quadrilaterals, I'll be doing a problem, a very interesting problem. Here you go. So you can pause the video and try the problem first. We are provided in the problem with BE and CF as the altitudes of triangle ABC, and we have O as the point of intersection. Let's call this O. Now we have to take any line KL through O with K on AB and L on AC. We have K on AB and L on AC. Perfect. And we have KM perpendicular to BE and LN perpendicular to CF. We have to prove that FM is parallel to EN. Now, forget the problem. First of all, when you see something of this sort, where you have to prove two lines to be equal, any two lines to be equal, immediately your mind should go on this diagram from middle school. You must have seen this, right? Two parallel lines and another one intersecting them. We used to call this what? Transversal, right? And when this used to happen, we had what? We used to find a lot of angles, pairs of angles. Let's say this one. Let me use a different color. Alright. So this angle is equal to this, and this also is equal to this. These two were referred as what? Alternate interior angles. This and this were referred as corresponding angles. So we used to find these pairs, alternate interior, corresponding, and they used to be equal. We were given two parallel lines. Now we have to prove that two lines are parallel. Now, can I say if I can find these angles to be equal, then I can conclude that the two lines are parallel? Perfect. So I'll have to find two pairs of maybe alternate interior angles or corresponding angles and then prove them to be equal in order to prove that FM is parallel to E. Now, what's the first requirement in order to find these angles? I need a transversal, guys. I need a transversal. Do we have a transversal? These are the lines that we are supposed to prove parallel. This is FM and we have EN, right? Notice that FN is acting as a transversal. FN, FN. These are the lines we are supposed to prove parallel, and FN is acting as their transversal. Let's just say. Now, if we prove this angle to be equal to this, are we done? That would be what? Alternate interior angles. If that happens, then we are done. We'll conclude that these are parallel. All right. So this is just a part diagram. We make this when the diagram gets difficult. Yeah. So you need to learn doing this. It's the same thing. These quadrilaterals. Now, I want you to spot cyclic quadrilaterals from the diagram. They're very easy to spot. Like you see this angle 90 and this angle is 90 as well. This whole thing, right? So the opposite angles add up to what? 180. So we conclude that the quadrilaterals MOFK and what else? This one as well. This one ELNO. These are what? Cyclic, right? So we have to chase this one angle. Alright. So by the theorem that we just studied, if you see this angle is being subtended by MO, so this will get transferred here as well because this angle is also subtended by MO. So these are going to be equal. Now, if you observe KM, this line KM, what's the goal? We need to transfer these angles to this quadrilateral, from this quadrilateral to this one, right? So for that, we'll have to observe KM. Notice that KM is parallel to ME, perpendicular to ME, and EL is also perpendicular to ME. EL is also perpendicular to ME. KM is also perpendicular to ME. So these two are perpendicular to the same line, ME. It is exactly like what we did in the session 1. The prime meridian and all the longitudes basically were perpendicular to the equator, and hence they were parallel, or as we assume in Euclidean geometry. So we are doing that. So we'll conclude that KM is parallel to EL. Right. Now since they are parallel, now we have got parallel lines, we'll look for what? Transversal. What's the transversal here? Look at KL. KL is acting as what? A transversal. KL. Right. And if you see Y is what? One of the alternate interior angles. Which one's the other? This. So Y gets transferred here. Perfect. Now observe, using the theorem, in this quadrilateral, which is also cyclic, I can say that this angle is also Y, right? This angle is also Y. Why? Because both of them are subtended by the same common chord, that is EO. So we have proven that this angle is equal to this. And that is what we needed to do in order to prove that FM is parallel to EN. And we're done with the problem. So I hope you understood at first the problem, and I want you to make remarks from this. So if you're supposed to prove two lines to be parallel, let's say any random two lines, AB or AB parallel to PQ, what's the first thing you'll look for? Transversal. Why? Because you need to prove some angles to be equal. You need to find something proving which will make sure that this gets proven. So what is that thing? That thing is angles. And for the angles you need what? Transversal. So first thing you look for is transversal. Then angle chase, using angle chasing, using techniques like this, spotting cyclic quadrilaterals, using congruency and all other things, you prove those angles to be equal, and then you conclude that the lines are parallel. So this is the sort of remark that you need to make from this problem. So whenever you encounter such thing, parallel proving in future, you should be able to do this. You must have heard of angle chasing, right? Today we are going to do area chasing. So what is it? Remember the beginning of the session, I showed you some of the problems, right? So how do you approach those problems? This is the way. So we'll be area chasing. So how are we going to do this? The core concept that is involved in problems of area chasing is spotting triangles with same height, or we can say common height. How do we do this? Let's say this is a triangle. This is the triangle ABC, and there are two triangles inside it. So we are interested in the areas of these two triangles. Notice that in those sort of problems, they always ask for ratios. Ratios like area of ABD by area of ADC, right? So we are going to switch ratios of areas to ratio of lengths. We'll keep doing this throughout this session, throughout this topic. We'll be switching from ratio of lengths to ratio of areas, and then from ratio of areas to ratio of lengths. How do we do this? This is the concept we use. We have to find triangles which have common height. Look at these two triangles, triangle ABD and triangle ADC, and look at this height. Let's call this XAX. Is AX the height of triangle ABD and also of triangle ADC? So if I have to write the area of ABD, that would be what? Half of BD to AX, and of ADC, if I have to write, that would be half of DC times AX. If you divide that, we'll end up with BD by DC. What is it? It's the ratio of the bases. So that is what we're going to generalize with this theorem that I've written here. But we have to first spot triangles with common or same heights, and then we concluded that the ratio of areas of such triangles is equal to the ratio of their bases. This is how. So this was level 1 that we were doing. So I'll write here ABD by ADC would be BD by DC. Now I'll need you to remember this configuration. This one, level 1. Because this will be used, this will be hidden, this will be embedded in problems, and you have to spot it, and then you have to use this thing. Perfect. Sweet. Coming to level 2, notice that you can spot the same configuration here as well. Not this, in triangle OBD and ODC. What we are interested in finding is the ratio of AOB to AOC in terms of lengths. You may want to pause the video and try this on your own. Alright. So if I just redraw the diagram, the same diagram, we have this triangle, and along with that we have, let's say this is D, this is O. We are interested in finding this. Can we say that OBD by ODC, the area, the ratio of their areas, would be BD by DC? From the first thing, from this. Alright. And can I also say that ABD by ADC would be BD by CD once again. Now what I want you to understand is, if you have P by Q equals R by S, these are two different ratios, exactly like this. These both are equal to the same thing, so they must also be equal. So they're like P by Q equals R by S. So we can write A into P plus B into R by A into Q plus B into S for any integers A, B, alright, belonging to the set of integers. This is a common ratio thing. If you didn't know, just note it down. So if I put A equals 1 and B equals -1, I'll end up with P minus R by Q minus S, right? So P for us was this, Q for us was this, and this was R, this was S. So if I do that, I'll get ABD minus OBD by ADC minus ODC. And what is it? If you observe, ABD minus this will be left with this area. Similarly, this minus this will be left with this area. And that is the ratio we were intending to find. And that is also what BD by CD. So we got a couple of things from here. Let me just erase this. I want you to note this down as a lemma, as an area lemma. From this triangle, we have OBD by ODC, OBD by ODC to be BD by DC. Also, AOB by AOC. This is also going to be BD by DC. So these are the two things. So remember this configuration as well. This you'll be using a lot in area problems. This will be helping you in all those sorts of problems. So yeah. Now comes a lemma. This is the first lemma from this course. So we have provided a triangle ABC, and there's this random line DE. There's no information provided regarding DE. It's not parallel to BC. Don't assume that. We are given the ratios. The AD is to DB is P is to R. AE is to EC is Q is to S. So when I put something in circles, you have to understand throughout the course that it's a ratio. Perfect. We are supposed to find ADE and the ABC, and the lemma says it's P into Q by P plus R into Q plus S. Alright. So we have to do the same thing. Spot common height. What triangles do we have to find relation between ADE and ABC? ADE and ABC. Now it's clearly visible that there's no common height, like ADE is so small compared to ABC. So what are we going to do? In such sort of situations, you're going to find a connecting triangle. What is a connecting triangle? It's a triangle that shares common height with both ADE and ABC. Alright, so we'll have to find a connecting triangle. How do you find a connecting triangle? One common thing that we do is we have to find connecting triangle between ADE and ABC, right? So we have to connect one vertex of ADE, anyone, you have to spot that on your own, and one vertex of ABC. So let's say if you want to do this, let me connect this. Notice the triangle ADC shares this height with triangle ADE, and also notice that this triangle shares this height with triangle ABC. Let me just redraw the diagram. Let me have a bit of space in here. Let me erase this, and I can draw a bigger diagram. Alright, so I was saying that this is the triangle This is DE, AB and C. I'm asking you to connect this. This is how you get the intuition for construction in proofs. So we have to find the connecting triangle. We found out that ADC is the connecting triangle. Why? Because it shares this triangle, this bigger triangle, shares this height with ADE, and let me change the color, and it shares this height with the bigger triangle. Alright, so in the first case, when this triangle shares this height with the smaller one, can I say that area of ADE by area of ADC would be what? Since they share the same height, the ratio of their areas would be the ratio of their lengths of bases. So the base for this small triangle is AE, and for this triangle is AC. Perfect. Now, from this height, because it's sharing the same height with the bigger triangle as well, so we can write ADC by ABC, the ratio of their areas, is also going to be the ratio of their bases. So in this case, this is the base for ADC, AD, and this is the base for this. Now, if you multiply these two equations, you'll have ADC cancelling ADC, and you'll have the required ratio that you intend to find here. And if you put the value of the ratios here, AE, if you notice, AE is Q, this is P, so that would be PQ, and AC is what? P plus R, Q plus S, and P plus R, here AB. Perfect. And that is how you'll end up with this lemma. Memorize this lemma, remember the proof as well. You can prove this using trigonometry as well. I'm not getting into that. I don't really like doing that. Alright. So based on what we just did, here's a little problem. So this is a really interesting problem. So you may want to pause the video and try this on your own. We're basically provided with three heights, right? Three heights of the triangle. It's not very difficult to notice that a triangle has three heights, of course. I hope you know that. And if you don't, please learn to use your brain a bit. So this has three heights. Any triangle has three heights. Here you go. And all those are concurrent, right? So yeah, we are provided with the three heights of the triangle HA, HB, and HC. We are given a random point in here, and we are connected. We have dropped perpendiculars from that point to all the sides, and we are supposed to prove that PD by HA, PE by HB, and PC by HC is 1. So the concept is same. Spot something common. How do you do that? First, look at what we are supposed to find. PD by HA. What is PD? This thing. HA is the height from H, from vertex H, right? PD is HA. Sorry, PD is this. So can we say that PD is the height of this triangle? PD is the height of triangle PBC, and HA of course is the height of the triangle ABC, right? Now if you notice the areas of PDC, triangle PBC, and area of triangle ABC, let me just write this. This would be what? Half. What about PBC? This is going to be PD, since PD is the height and the base is BC. For this, it's half HA into BC. This is going to cancel. This is also going to cancel. So we're left with this. So what we can realize from this problem is it's not always the common height. It may also be common base. In this case, we had the common base BC. For both of the triangles ABC and PBC, the common base is BC, which will get cancelled, and the ratio of their areas would be the ratio of their heights. So what we have here in the problem, in order to prove this, I'll just write this in terms of areas. I told you in the beginning, we'll keep shuffling, we'll keep switching from ratios of lengths to ratios of areas. That is how we solve these problems. So PD by HA, I can write PBC, area of PBC by ABC. Similarly, PE is the height of triangle PAC, and in the denominator we have again ABC plus PC is again what? Have I written PC? It's F, sorry. This is F. So PF is what? Area of PAB by ABC. So if you add this, you'll realize since the denominator is same, these three are gonna add up to ABC. We'll have ABC by ABC, and that is 1. The theorem, the problem is proved, and we derive a conclusion from here. You may want to write this. So for any triangle and for any random point inside it, if you drop 3 perpendiculars from that point, the height of those perpendiculars, the ratio of heights of the triangles and those perpendiculars is going to add up to 1. So I'm going to say, let's say this is DEF. So the same thing actually, same thing. Remember that as a theorem, as a lemma, or whatever you wish to call it. Remember this. Now we come to one really interesting problem on area chasing. Now this problem I won't be spoon feeding you. I won't be really showing a lot of writing here. I'll be doing it inside, and you'll have to learn how to do that, how to get that fast. First I'll be doing like that, and then I'll be explaining a bit, so you don't need to worry. We're provided with a really interesting diagram. This is the best thing I've ever made. No, I've made better things. My handwriting looks better. Anyways, we are provided that AB dash is 2AB. We have AB dash as 2AB. So if we just consider, wait a minute, let me just change the color. Let me just zoom in the diagram. So we have AB dash as 2AB. So if I consider AB as A, AB dash would be 2A, AB dash. What would be BB dash? That would be A, because this whole thing is 2A, this is A, this make this A. Alright, perfect. Now, we have CC dash given to be 2BC. CC dash is 2BC. So if I consider this as B, this is gonna be 2B, right? Apart from that, we have AA dash as 3AC. So if AC is C, AA dash is gonna be 3C, right? We also provided that the area of this triangle is 1. So the area I'm going to put into boxes and the lengths into circles. Perfect. So if you notice, the ratio of this is same, like 1 is to 1. A is to A is 1 is to 1. Also notice that this triangle, the area of this triangle and this triangle would also share the same ratio. So if this is 1, this is also going to be 1. Exactly like that. This is C, this is 3C. The area is 1. Here we're going to have 3 as the area. I'll explain. I'm just doing this the way you should be doing after a couple of like hours of practice. So yeah, this is 3. This is also going to be 3. Why? Because it's same. All right. Let's get to this. This is 1. And since the ratio is 1 is to 2, this is going to be 2. Perfect. Now let's get to this one. This is the ratio is B is to 2B. That is 1 is to 2. This is 1. This is also going to be 2. Now coming to this triangle, the ratio is 1 is to 3. This is 2. So this is going to be 6. I guess we have all the areas. We had to find the area of the bigger triangle. We'll just sum it up. So it's 3 plus 3. It's 1 plus 1 plus 2 plus 2 plus 6. This is 6 plus 6 plus 6. That is 18. That is our answer. How do we do this? We provided that the area of this small triangle is 1. I want you to focus on this triangle. Look at this. We have the same height. We have a common height between these and these triangles. This and this. So the ratio of the areas would be what? Ratio of the areas would be the ratio of their bases. Ratio of their bases is given to be 1 is to 3. C is to 3, C is 1 is to 3. So if the area is 1, the area of this triangle is going to be 3. That is what I did here. Exactly like that. In this triangle, you have this common height, right? Now since this area is 1, this is also going to be 1 because the ratio of the bases is same. Now in this triangle, let me just change the color. In this triangle, look at this. The height is same. Are you able to observe the height, the same height? For both of them, the height is same. It will have to extend the base in order to look at the height of this triangle. This is the height. For this triangle as well, this is the height. Perfect. So if this area is 3, if this area is 3, this is also going to be 3. Now, coming to this triangle, this one. The ratio of the bases is b is to 2b. Once again, I'll have to extend the base in order to look at the common height. This is the common height for those two triangles. You don't have to draw the common heights and stuff and write areas while you're in the exam hall. You have to do exactly like this. This is what you call as area chasing. Wow. Okay. So exactly like that you do this in this triangle and you end up with this result. I've got one more problem on the same topic on area chasing. Let's see if you can do that on the lemma that I just told you. The area lemma at first and then the second lemma regarding that PQ by something something. P plus R into Q plus X. Q plus S. You have to use that in order to figure this out somehow. Alright. So we have to find X and Y. These are the areas actually. 40 and 30, these are areas. We have to find X and Y. So if you observe, let's say this is D, this is O. If you observe, area of ADB and area of ADC would be what? BD by DC, area of their ratio of their bases since the height is same. What is BD by DC? We don't know yet. Can I also write that as area of OBD by ODC from these two, right? It's also going to be that. And this is 4 by 3, right? So I can say that ADB, area of ADB and ADC, the ratio is going to be 4 is to 3. So if you notice, area of ADB is what? 84 plus Y plus 40. Of ADC is X plus 65. I'm just adding the areas. That is 43. You get one equation from here. If you observe the same triangle from a different perspective, from here, can I also say, let's say this is E. Alright. Let's say this is E. Can I say area of triangle ABE by area of triangle CBE is AE by EC, right? And what is AE by EC? It's also going to be the area of triangle OAE and area of triangle OEC, OAE and OEC, and that is X by 35. So this is going to be X by 35. What is this? This is X plus Y plus 84 by 40 plus 30 plus 35, that is 105, and that is what? X by 35. This is the second equation that you got. Solve these and you'll have X and Y. So this is how you use area chasing. I hope you have learned this and you'll master this through some practice. This is an amazing concept that keeps appearing in Olympiad geometry, especially area finding. So there's more to this. We'll be discussing a lot more stuff regarding this. All right. So this was basically the part 1 of tackling those area problems that I showed you in the beginning. In the next session we'll be continuing this. That would be the part 2, and we'll be learning really amazing, very original lemmas that you won't find anywhere. So I'll suggest you stick to this. All right. In today's session, what we did was, first, parallel lines thing. What do? We look for transversal. Second was area chasing. We look for common what? Common height. And also we learned that there can be common base as well from that problem. Apart from that, we also learned to find connecting triangles if we cannot find common height or common base. Right? And apart from this, of course, we learned how to spot cyclic quadrilaterals. That was it for today's session. I hope you really enjoyed this one. See you soon.